Size changes is what we're talking about today. And like I said, I'm going to be jumping back and forth between this and the document camera because when we get to the examples, I'm going to actually write out the examples with you. Can you guys do me a favor and put the rulers down? Right? All of you who are spinning and fidgeting and playing, it's very distracting to me, which probably means it's distracting to your classmates. So, okay. Yeah, it did. Okay.
Would you like to speak?
Spanish.
All right. The transformation. Okay. A size change transformation. And a size change is just like what it sounds. It's when you're taking a figure and changing the size of it. The mathematical notation will look like this. It'll be an S with a number underneath it. That number underneath it we call K. Okay? And it's, yep, Bryce?
Take away the what?
The stuff on the side.
Yeah.
I don't know if I can, but what I can do is that.
Oh.
Shrink that. Does that help?
Yeah.
Okay. Sorry, I forgot you had to write that down. A size change transformation, written S with a subscript K, is found by multiplying the coordinates of the pre-image by the magnitude, K. You're going to see that K pop up a lot in this chapter.
Okay.
Okay? Okay. Okay, so the example we're going to do here, it says draw the segment with these endpoints, 3, -1, and -1, 2. Then draw the image under S2. So let's start by just drawing the segment. So 3, -1. I'm going to go 3 to the right and 1 down. It's here. And that's point A. And then point B is at -1, 2. So up here. Draw that segment. Okay. When I say draw its image under S2, that S2 means to multiply each of the coordinates by 2. And then graph those points. So that first one, 3, -1, would become 6, -2. 3, 4, 5, 6, and -2 is down here. And so this would be A prime now. B would be -2, 4. Okay, so that's B prime. Connect those. So that red line, the red segment, is what I would call the image under a size change with factor or with magnitude 2. Okay? So what do you notice? What do you see here?
Bigger.
Okay, I heard, Bryce, what did you say? Okay, so the segments are parallel.
Looks like it makes a trapezoid.
Okay, that's true. Because if the segments are parallel, right, you would have one pair of parallel sides. What else do you notice? I heard someone say it's bigger. How much bigger do you think it is?
Bigger.
It's 2 times as big. Yeah. 2 times the length. Okay. Which would make sense, right? If it's under a size change of 2, that the length would be doubled. Anyone see anything else? Bryce, what are you saying? Okay, that's just sort of because that's how the coordinates started, but good thinking.
If you make a trapezoid, the segments are congruent.
Not necessarily. I see what you're
Well, if
saying.
they're parallel,
The red one and the gray one are parallel, but the other two segments wouldn't be. Okay? Look at this. This is one that you probably wouldn't necessarily see. But if I put a dot here at the origin, do you see that these points are all in a straight line? Okay? And also, let me get a different color. I could connect these points and these would all be in a straight line. Oh, where'd my color go? Okay. So every point with its image is collinear with the origin. Okay.
Points are collinear.
Point and image. So that means the old point and the new point. Hector, no.
Where do you want me to sit?
That one right there that you're standing right in front of. I'm going to finish writing this and then I will get you a notes packet. Okay. So if you connect every point with its new image, it's going to make a straight line that goes through the origin. Well, you're just right here in that first example. Okay? So that's what happens when you do size changes on the coordinate plane. We okay with that? Okay. This next part, I give you this because I want you to see what the definition actually says, but it's kind of complicated. Okay? It's going to make much more sense once you see it. So, definition of a size change, and I think I left this in there for you because I didn't see much value in you copying it down. So O is some point somewhere, and K is a positive real number. And K, remember, stands for the magnitude of your size change. Okay? So if you take any point in a figure, okay, you can make a size change with it by taking the ray from O to that point and multiplying it by K. That's basically what that second line says. Okay? And so then we would call that movement a size change with center O, and then the magnitude would be K. See what I mean? Sounds confusing? It'll make much more sense once you see it. Okay, but I wanted you to have it in words. When that K value is bigger than 1, think about what we just did. Our K value a second ago was 2 because we multiplied the coordinates by 2. Anytime that K value is bigger than 1, is the shape going to get bigger or smaller?
If it's 1, wouldn't it stay the same?
Yes. Yeah, and that's going to be down here at the bottom. But if it's bigger than 1, what's going to happen to the figure?
It's going to get bigger.
It's going to get bigger. We call that an expansion. Okay, so anytime that K number is bigger than 1, you can expect the figure to get bigger than the original one, and we call that an expansion. What's going to happen if K is less than 1?
Decretion.
Contraction. What kind of numbers are less than 1?
0.
Okay, I heard 0 and I heard negative.
0.5.
The problem is if you multiply by 0, aren't all your coordinates just going to turn into 0? Okay, and we set up here that K has to be a positive number. So if it has to be positive, can't be negative, and it can't be 0, what kind of numbers are we talking about? Fair enough? Decimals, yeah, decimals are fractions. So if I give you a K value that's like 0.7, you can expect your shape to get smaller. And then what Bryce said a second ago, if K is exactly equal to 1, if you multiply by 1, what's going to happen? It's going to stay exactly the same. The identity transformation. Okay? Identity is anything that brings something back to its original. Okay? So if I multiply all the coordinates by 1, it's going to just stay in the exact same spot. Now here's what we're going to do. The next couple of examples I'm going to do together with you on the document camera, but I would like to flip all the way to the very last slide and fill that in using the iPad, and then that way I'm not flipping back and forth a bunch of times. Skip ahead past the next few examples to this slide, size change properties, and then we're going to go back and do the examples together up here on the screen. Okay. Do you remember when we did transformations before? Give me an example of something that's a transformation.
Live reflection.
Okay, there we go. Live reflection, translation, rotation. Okay, do you remember how we talked about those things preserving certain properties? Do you remember what those things were?
Yeah.
Orientation.
Oh, only some.
Okay, some of them preserved orientation. Yep.
Reflection.
What other things were preserved?
Shape. No.
Remember A, B, C, D?
Oh, angles.
Angle measure
Between this.
between this.
Polarity.
Collinearity and distance. Okay, when you do a size change, almost all of those things are still preserved. Okay? A size change, remember, is going to be making something bigger or smaller. When you do that, if you do it proportionally, which is what a size is, angle measure is preserved, betweenness is preserved, and collinearity is still preserved. Okay? I don't remember. It's a hard one to say. Collinearity. The only thing that's not preserved is distance, which makes sense, right? Because the whole point of what you're doing is to make the space between these 2 points bigger or smaller, okay? But how much bigger or smaller? Well, that's always going to be determined by the value, okay? And I'll make that so you can see it. Under a size change with magnitude k, the distance between any 2 points on the new image is k times the distance between the same points on the pre-image. Okay. So if I take a shape, name a shape.
Triangle.
Square, okay.
Cylinder.
So if I take the 2 corners of a square and measure the distance between them, and then I take that square and I do a size change, so I make it bigger by whatever k is going to be. Okay, so I make it bigger. Now the distance between those 2 corners is going to be k times whatever the distance used to be. That's what that's saying. Okay, so basically all of your distances get multiplied by k. Okay, and remember k is that size change factor, that ratio. Okay, the one example we've done so far was S2, and that meant we multiplied everything by 2. Bryce, question?
I was wondering, what was orientation again?
Orientation was like the direction that the shape was facing. Like, do the points still go in order or are they reversed?
So what
Under a size change, yeah, I guess orientation would still be preserved. Yeah. That's not one that they really identify necessarily, but you're right that it would still be preserved. Yeah, because there's not any reflections going on. Questions on any of that before we do the examples? Seem to make sense so far?
Yeah.
That was 3 lessons. Okay, let's do some examples together.